Hello, everybody. So what we're going to be looking at today is section 5.3 in your book, which is structural induction. So that's a new topic, familiar to you, right? It's going to be a lot like the other forms of induction that we've already seen, but it's a new thing for us. But before we do that, we're going to go over one last thing from section 5.2 that we didn't go over. Um, yeah, so this is going to be something having to do with polygons. It's not going to be super important that you know, but it's just kind of an interesting thing that you might want to see. So this is going to be from 5.2 still. Dot dot dot. All right. And so in order to do this last example from 5.2, we need to know what a polygon is. So I guess definition, a polygon, and I'm not gonna, there's gonna be some problems with this definition. It's not gonna be like super precise, but it's good enough to get the idea. So hopefully you'll be okay with this. So a polygon is, let's see, I should rewrite this actually, an insided polygon. An insided polygon is a shape with, let's say, invertices, which are going to be the corners of your polygon. Corners called, and you don't have to give them names, but I am for a reason, V1, V2, V3, dot, 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 up to Vn, and edges that connect V1, that says V0, V1 to V2, V2 to V3, dot, dot, dot. You get to the end, right? We're going 1 to 2, 2 to 3, 3 to 4, 4 to 5, etc. Eventually, you're going to get to the end of this list, and you're going to go V to n minus 1 to Vn, and that's not the last edge. The last edge is actually Vn back to V0. Okay, and so that's what we're going to use just as our definition. I said V0 again, but I meant V1. And that's just what we're going to use for this definition, and it's going to be good enough. Okay, so we can draw a couple of examples to make sure we know what we're looking at. Examples. Three-sided polygon. Four-sided. Six-sided. What do these look like? Well, I mean, you know what they look like, right? So just using the definition, if I'm making a three-sided polygon, then I should have corners, which I'm calling vertices, V1, V2, V3, and then we have edges that connect them. So V1 to V2, like that, then another one V2 to V3, like that, and then when you get to the last number, so in this case V3, then you should connect that edge back to V1. So that's a triangle. Okay, three-sided polygon. All right, and that's all we're doing. So like a four-sided polygon, you have V1, V2, V3, V4, and 1 connects to 2, 2 connects to 3, 3 connects to 4, and when you get to the end of the list, 4 connects back to 1. And so that's how these are. Not really a lot of mystery here. That's just what we're going to use for a definition of what this is, right? The problem with things like shapes in math is that you already know what they are, but you need a precise mathematical definition of a thing that you already understand. And it's sometimes tricky just to come up with the definition. But there we go. So those are some insided polygons. Okay. Um, Now then what we want is we want to talk about a triangulation of a polygon. And I don't even know if this is really going to have a definition. But what we're going to do is we are going to, I'll give you the idea of it. Idea. Um, in, I'll say like computer graphics, it's common to triangulate a polygon. So what's that? Well, triangulation is when you split a polygon into triangles. It is to split a polygon into triangles. And there's multiple ways to do it. So like if I take, let me just copy and paste this. Duplicate. So like if I take this, I'm going to duplicate it again. And we'll duplicate it one more time. All right. So here are 3 polygons. And if you wanted to, you could split these into triangles a lot of different ways. So like, for example, if I add a few new edges here, like if I add an edge there, and I add an edge there, and then I add an edge there, now that entire thing has now split up into triangles, right? There's a triangle here, 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 and then one in the middle. So that's all triangles. But that's not the only way to do it, right? You could split it up a lot of different ways. You could split it up this way. And then you've got, oops, got a side there, you got a side there. I'm not going to color these in super good. Triangle, triangle. But those again, they're not the only ways to do it. Even these, right? I could put a line down there, and then I could do that, and then I could do that. And that's another triangulation of this 6-sided polygon. Okay, so there are a lot of ways to do it, but you can do it. And there's actually a theorem that says you can do it. Okay, and so that theorem is proved with an induction proof, a strong induction proof. So again, you're not going to hopefully have to do a proof like this, but you might be interested in seeing how you can prove that you can do this. So let's try this. So here is our thing. Example. What we're going to do is we're going to prove that every simple polygon now I didn't define simple up there, but simple is going to mean that you can't have this kind of polygon. Like that can't be your 4-sided polygon where you have a corner, 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 and then you have the sides cross. So we can't have the sides cross, but I didn't say that up there. So maybe I should have said that. So I only drew simple polygons. So that's what we're not allowing. Every simple polygon with n equals 3, 4, 5, ... sides can be triangulated into n-2 sides. Okay, that's what we want to prove. However, there's a reason that we can't do it yet, because there's a lemma that we're going to need. So I'm going to write this down for you, and we're not going to prove it, but we will, I think you'll accept that as true. So, um, lemma. So what's a lemma? Remember, a lemma is a theorem that you're only proving because it's going to help you prove another theorem. So a lemma. Um, every, that doesn't say every polygon, I should say simple to keep it correct. So every simple polygon with n greater than or equal to 4 sides has an interior diagonal. And I'm not even going to define what an interior diagonal is. But well, maybe I will. Has an interior diagonal. What's an interior diagonal? That is um, a side that a new side. Edge, new edge that can be made. I'll say added between vertices that was not already there. That is interior to the polygon. And again, I'm not going to define all these terms. Like, I'm not going to define in interior, but one of the ideas with a polygon is that there's an inside and an outside for a simple polygon. So here I'm going to draw a polygon. Looks like we got 5 sides on this one. That's not what I wanted. All right, so there's a 5-sided polygon, right? And so we know that there's already certain edges there, right? Like V1 to V2 and V2 to V3 and V3 to V4 and V4 to V5 and V5 back to V1. And so there's an inside and an outside to this polygon, right? Outside or exterior. And then there's an interior to the polygon as well. So every simple polygon, right, where we don't allow the sides to cross, has an inside and an outside, and an interior diagonal would be a new edge that you can be added between vertices that was not already there. And so what would that look like? Well, all I'm saying here is an interior diagonal would be, for example, if you just take this side and this side, just any two of them, you can add an edge. And there you go. That's an interior diagonal. Oops. And the claim of this lemma is that as long as there's 4 sides, you can do that, which should make sense, right? Like if you take a 3-sided polygon, then there is no interior diagonal to a 3-sided polygon because you've already, like, if you're going to start from here, where do you add the edge? Well, you've already got edges to the other 2 corners, so you can't add a new edge to a triangle. But if you have at least a rectangle, then there would be a place where you could add the interior diagonal. So as long as there's 4 sides, you can do that. Okay. Now, again, I'm not going to prove that. I'm just stating it. If there's 4 sides or more, then you have an interior diagonal that you could add. Okay. And you need that before you do this proof that every simple polygon can be triangulated into n-2. I wrote sides. That's the wrong word. We're triangulating. Triangulated into n-2 triangles. Okay. So what would the proof look like for that theorem? So we're gonna prove. How does it look? So we know that for an induction proof, so this is going to be the triangulating, not the interior diagonals. Right. That's the theorem. So what's the basis step? So the basis step would be where you show that an n equals 3-sided polygon can be triangulated um, into n minus 2 sides. So let's see. Consider n minus, no, not n equals 3-sided polygon. Right? There it is. It's a triangle. Right? Um, so it's already been triangulated. So it obviously can be triangulated into n minus 2, which is, what's n minus 2? Well, if n is 3, right? N is 3, then n minus 2 is going to be 1 triangle. Can it be triangulated into one triangle? Yes, of course. It is one single triangle. So that's it for the basis step. A triangle can be triangulated into a triangle. All right, cool. Now, what's the induction step look like? Right, that's going to be the tricky bit. So for the induction step, we have to have an induction hypothesis. So for the induction hypothesis, we're going to assume that every every polygon from 3 up to k can be triangulated. So we have to assume every polygon with n equals 3, 4, 5, up to k sides can be triangulated into n minus 2 triangles. Right? That's the induction hypothesis. Now, what do we need to show? What we need to show is that we can find a triangulation for a k plus 1-sided triangle. So our job here, our job is to now show that any k plus 1-sided triangle or polygon can be triangulated. Now, specifically, we need to show that any k plus 1-sided polygon can be triangulated into how many triangles? Well, it would be n minus 2, right? So if it's k plus 1-sided, then subtract 2, you'd have k minus 1. So it can be triangulated into k minus 1 triangles. That's what we are hopefully going to show. All right, so that's what we need to do, and we haven't done it yet. But we have our induction hypothesis, right? Up to k, we know you can do. K plus 1, that's what we're proving. Okay, so how would you do that? Well, to actually start the proof here, you say let P be a k plus 1-sided polygon. And so something about these kinds of proofs is that a picture is never a proof, but a picture can definitely help you understand what's going on. But you have to be careful when you draw a picture, because the picture that you draw might not actually be the only possible case, but you might think that it's the only possible case. Like back up here, when I was drawing polygons, right? I said an insided polygon, and I said looks like this or this or this kind of thing, right? Um, and that's because I wasn't thinking about what if I drew it with sides crossing like this one. Well, I didn't think about it, but that could have happened, right? Um, so you actually needed that some definition of a simple polygon, which I didn't even write down, but that said that the sides were not allowed to cross each other. That'd be a simple polygon, right? But what if I had written all this stuff without the word simple? Then I probably would have kept drawing these kinds of pictures, and I would not even have thought about this right here, even though it was a possibility. And so you have to be careful with pictures that your picture actually describes what you like, all of the possible cases. So let's say let P be a K plus one-sided simple polygon. I'll even change it. Simple polygon. So I'm just going to draw just a polygon here. It doesn't matter how many sides it has. But we're going to write down how many sides it has. That way we can just keep track of the numbers here as we go. So how many sides did I just draw? 1, 2, 3, 4, 5, 6, 7, 8. So that's an 8-sided polygon. Actually, I counted the vertices, but the edges should be the same, right? So that is an 8-sided polygon. Okay. And you're supposed to show that an 8-sided polygon can be triangulated into 6 triangles, right? N minus 2. So there's just an example K plus 1 sided simple polygon. Now, the idea is if you have a K plus 1 simple sided polygon and K is at least 3, right? Because we're talking about 3 up to K, and this is K plus 1. So if this starts at 3, if the smallest K could be is 3, and we're at K plus 1, P has to have at least 4 sides. P has at least 4 sides. Now, what does that mean? Well, if it has at least 4 sides, then P must have an interior diagonal. So by the lemma that we did not prove, P has an interior diagonal. Okay, now where's the interior diagonal? The interior diagonal could be anywhere. Sorry, I'm waiting for something to scroll off my screen so I can write again. Okay, so where's the interior diagonal? Could be anywhere, right? So like, it could be right there. That's an interior diagonal. Or it could be right there. That's an interior diagonal. Okay, so it does not matter where it is, but one of them has to exist. Okay, now according to my notes here, we're going to call that interior diagonal is going to be called AB. And the idea is that the corners that it's connecting are side A or corner A and corner B or something like that. All right, so by the lemma, P has an interior diagonal. We'll call it AB. Okay, so there we go. Now, so what this does is it actually splits our polygon into 2 smaller polygons. This splits polygon P into 2 smaller polygons. We're going to call them what? Q and R, I think. All right. And let's also say, suppose Q has S sides. S is a number. And R has T sides. Right? And we have to do that because we don't know actually how many sides, um, you know, we've split this into, because we don't know where the interior diagonal is. And so the idea, just based on the picture that I've got here, is that the two polygons, right? One of them is, you've got AB here, and then you've got that. And so that's your Q. And then the other one also has AB as one of its sides. And then that's R, right? So we're just cutting it at AB. All right. So this splits polygon P into two smaller polygons, Q and R. Suppose Q has S side and R has T sides. All right. So there it is. What we need to do now is count up all of the sides. Okay. Let's see. So together, Q and R contain all of the original sides of P, right? So all of the blue sides are here, right? All of these blue sides are here in R, but they both have AB, right? They both include this new side, AB. So if you actually are counting up the sides, you have the number of sides of P, which was K plus 1, and then actually there's two extra sides because there's AB, but AB is actually counted as part of Q and part of R. So it's two extra sides to the sides that we did have. So Q and R contain all the original sides of P. And two more. And that's because AB is included in both, in Q and R, so it would get double counted. Okay, so there you go. So we've split this polygon P into two smaller polygons, and we know how many sides it has. That means if we add up the sides of Q and R, the S and the T, remember we said Q had S sides and R had T sides. So S plus T is equal to the K plus 1, that's how many sides that P had, plus 2, because it's plus AB plus AB. So that's plus 1 plus 1. So total S plus T must be K plus 3. Okay? So we're just going to keep track of this fact now. In fact, maybe I'm going to highlight this right here. And hopefully this made some sense here. So you agree that, the number of sides of Q and R add up to K plus 3. Okay, so then what are we going to do? Well, what we're going to do now is we're going to look at the polygon Q and R. So Q and R are now two polygons with fewer than, with K or fewer sides. Yeah. So Q and R are both polygons with K or fewer sides, and also 3 or more. And I don't really want to spend a lot of time justifying that. But so just thinking about this, if you come up here, we didn't say it, we never said it anywhere, but if you take a polygon and you put the interior diagonal like this, then the smallest you could split Q or R into would be like this size right here, right? A three-sided polygon. Okay, and so the fact that the smallest Q or R could be is 3, that should make sense just based on the fact of if you put an interior diagonal, you're going to get a triangle minimum. But then the fact that they have to add up to K plus 3 sides means that if Q had 3, then R would have to have K to add up to K plus 3, right? So they all have 3 or more, and they all have K or fewer out of Q and R. So they might not look at the picture I drew, but they have that property. 3 or more, K or fewer. So Q and R are both polygons with K or fewer sides and 3 or more sides. All right, that means the induction hypothesis applies to them. So that means that they both can be triangulated. So by the induction hypothesis, Q can be triangulated and R can be triangulated into how many sides? Well, remember, Q has S sides, so its triangulation would be S minus 2 triangles, and R has T sides, so its triangulation would be T minus 2 triangles. Okay, tries. So by induction hypothesis, Q and R can be triangulated into S minus 2 and T minus 2 triangles, right? Well, if you can triangulate Q and R, right? So if I can triangulate Q and R, let me copy Q and R. Duplicate down here. So now you can triangulate Q and R by adding, or well, just by triangulating them, right? So I don't have to do anything to prove this because by the induction hypothesis, this is possible. So now you've triangulated Q into S minus 2 triangles and T minus 2 triangles. And so if you can triangulate Q and R, then you put them back together and you have a triangulation of P, the original polygon. So put them together. And you have a triangulation of P. With how many sides? Or sorry, how many triangles? Well, how many triangles? We know that Q has S minus 2 and R has T minus 2. So if we ended to add them up together, we would have S minus 2 plus T minus 2 sides, right? S minus 2 plus T minus 2 sides. So how is that together? Add those up, and what we have, I said sides. I keep saying sides when I mean triangles. S minus 2 plus T minus 2 triangles. So that's it. But how many is that? Well, S minus 2 plus t minus 2 is equal to s plus t minus 4, right? S plus t minus 4. And what's s plus t, though? S plus t is k plus 3, right? The bit that I highlighted there. S plus t is k plus 3. So that is k plus 3 minus 4. And this was triangles. So that is k minus 1 triangles. So what did we just show? Well, we just showed that way back up here, P was a k plus 1 sided polygon, and we just triangulated it into k minus 1 triangles. That's what we were trying to do. So the k plus 1 sided simple polygon P was triangulated. That's bit. Triangulated into k minus 1 triangles. Right. That's what we were trying to do for that induction step. So we're done. We can make our conclusion, which is every n equals 3, 4, 5 up to k. No, just every 3, 4, 5 up to forever sided simple polygon can be triangulated into n minus 2 triangles by induction. Okay. And that's the proof. So all I want to say about this now is just to hit the high point, scroll back up here. So the algorithm for how to do this, right, was how do you split a big polygon? Well, you cut it in half into 2 small polygons. And then the induction hypothesis tells you that you can take the small polygons and triangulate those. So how do you triangulate a big polygon? Split it into small polygons and then triangulate those. And so that's all we did. So if you can triangulate a small polygon, you can triangulate a big polygon. And we just counted up the number of triangles it would take, and it worked out, right? So like a k plus 1 sided polygon ends up with k plus 1 sided polygon ends up k minus 1 triangles, which is what the theorem said. So that's it. We did it. That's our proof. Is it a tricky proof? Yes, it is. Does it require you to keep track of a lot of different numbers all at the same time? Yes, it does. But it's worth, spending some time trying to understand that. It's a long proof. Even typed up, it's like a full page or more. It's in the typed up notes for this, so you can read it there if you want. And yeah, that's it for this this proof here. So I'm going to stop the lecture here, and then actually the next video, which is also going to be posted at the same time as this, is actually going to be 5.3. So this was still 5.2. So this is 5.2 in video 1. Okay, so that's it. So 5.3 in the next video. Talk to you next time.